Previously, we covered the core foundations. Now in part 4, we tackle, is Mars actually possible? The real story of getting humans there. Episode 4. Elon says 2029. What does the science actually say? Public timelines are bold. Engineering schedules are ruthless. Those two things rarely arrive at the same destination at the same time. Last episode, we looked at what a crewed Mars mission would actually demand from the human body, the radiation, the isolation, the physiological cost of getting there. Today's question is different. When? And more importantly, is the when being talked about publicly anywhere close to what the engineering actually supports? This is episode 4 of Is Mars Actually Possible? And we're getting into the timeline problem. Section 1. The dates on the table. You've almost certainly heard the number. Elon Musk has publicly stated a target of getting humans to Mars by 2029. SpaceX's own roadmap has referenced uncrewed Starship landings as early as 2026, with crewed missions to follow within a few years of that. Those are publicly stated targets, and that distinction matters. A target is not a schedule, and a schedule is not a guarantee. In the history of complex space programs, ambitious early timelines have almost always shifted. The Space Shuttle, the International Space Station, Artemis, all slipped, sometimes by years. That's not a criticism. It's simply how large-scale engineering works. When you're building systems that have never existed before, reality tends to renegotiate your calendar. So let's look at what actually needs to be true, from an engineering standpoint, for a crewed Mars landing by 2029, or realistically, any time in the early 2030s. Section 2. The critical path. Several things have to work, not individually, but in sequence. Miss any one of them, and the mission doesn't happen. First, heavy lift reliability. Starship is SpaceX's vehicle for Mars. It's the largest rocket ever attempted, and as of 2025 into 2026, it's been making genuine test progress. But test flights aren't operational missions. You need a consistent track record of reliable launches before you put a crew on top of it. That record takes time to build. Second, in-space refueling. A Mars mission using Starship requires multiple propellant transfer operations in Earth orbit. Tanker spacecraft moving cryogenic fuel to the mission vehicle before it departs. This hasn't been demonstrated at operational scale yet. It's on the roadmap, but it remains one of the less mature elements of the whole architecture. Third, entry, descent, and landing at Mars. At the scale a crewed mission demands, Mars has a thin atmosphere, roughly 1% of Earth's. Too thin to slow you down easily, too thick to ignore entirely. Everything we've successfully landed on Mars so far has been relatively small. A crewed Starship would be arriving at perhaps 100 times the mass of anything we've put down there before. The engineering challenge scales dramatically, and it hasn't been solved yet. Being worked on, yes. Solved, no. Fourth, surface power and life support. Once you're there, you need reliable power, breathable air, and water. Sustained over months, possibly longer. NASA's MOXIE experiment on Perseverance did demonstrate that oxygen can be extracted from the Martian atmosphere. That's a meaningful proof of concept. But a small-scale demonstration and a full life support system for a human crew are very different things in terms of scale, redundancy, and long-term reliability. Section 3. What the science says about readiness. NASA's human spaceflight program has been developing Mars architecture for years. Their CAPIA program, Crew Health and Performance. Exploration Analog runs ground-based simulated Mars missions here on Earth, studying how crews cope with isolation, limited resources, and communication delays measured in minutes each way. The first mission completed in 2024, with a second in planning. Valuable work. But these are analog studies. They tell us about human factors. They don't replace the hardware that still needs to be built and flight tested. If you look at technology readiness levels, the standard scale NASA uses to assess how mature a given technology is, several critical elements for a crewed Mars mission are still sitting in mid-range development. Past early concept stage, but not yet flight proven. The honest answer to, what does the science say about 2029, is this. It's possible in the way most ambitious goals are possible, meaning it can't be ruled out in principle. But the number of things that would all need to go right, on schedule, without a single major setback, makes it a very low probability outcome for that specific year. Independent analysts more commonly cite the early 2030s as a realistic window, and even that carries significant uncertainty. Section 4. Why this matters beyond the date. Here's the thing. Whether the first crewed Mars landing happens in 2029, 2033, or 2040, the date matters, but it's not the deepest question. A landing is a moment. A colony is a civilization-scale undertaking. Once humans have stood on Mars, the harder challenge begins. Can they stay? Can others follow? Can it become something permanent? That's where every technical challenge from this series converges. The radiation, the physiology, the life support, the supply chain across 300 million kilometers, which is exactly what we're getting into next. Part 5 asks the biggest question in this whole series. Could humans ever actually live on Mars permanently? And what would that genuinely require? If you found this series useful, subscribing means you won't miss it when it lands. We'll see you there. That is part 4 of Is Mars Actually Possible? The real story of getting humans there. In part 5, we explore the next key question. Subscribe so you do not miss it.